Okay, in part one, we convinced you that machine learning is used in every second of your daily life. Here in part two, we'll review some basic components of machine learning algorithms and look at various scenarios of machine learning. And at the end, we'll list the topics that we'll cover in the rest of this course. So first of all, what is machine learning? Well, machine learning can be best summarized as automating automation, which is very cool because computers are there to do the automation, right? Computers is all about automation, but this kind of automation requires programmers to explicitly write down the specific rules for certain tasks, right? For example, think about a task of translating from English to Japanese. Okay, for example, I love Oregon is translated to this Japanese phrase, the Japanese sentence. Now, in order to do that, you need to know that in English it's subject, verb, object, but in Japanese it's subject, object, verb. So that kind of specific knowledge should be encoded by the programmer into the translation program, so which we often call a rule-based translation. So that is a very typical AI program before machine learning. In machine learning, however, we flip output and program so that you don't need to write the programs yourself. You let the computer learn from data. So what is data? The data has input and output pairs. For example, English and its Japanese translation, another English sentence and its Japanese translation. And let's say you have 1 million of those sentence pairs. One English, one Japanese, one English, one Japanese. And somehow there's a magic program that is a machine learning program that learns from that data and output an automatic translation program. And that is actually how Google Translate works. And that is actually how every single translate service nowadays works, right? It's not possible to write computer programs to translate between every single language in the world to some other language, right? You have to use data to do this automatically. So that's the power of machine learning. That does sound like magic, right? But it's really not magic because you just need a seed, which is your learning algorithm, and then feed it with a lot of data, that is the nutrients. And eventually you'll get results, which is the program, right? And there's a famous quote that there's no better data than more data, right? So data is really the key in machine learning. Well, some people think machine learning algorithms is the key, but often the difference between different algorithms are not so different. And if you feed it with twice as much data, you'll get much better results. Now, there are tons of thousands of machine learning algorithms published every single year, but every machine learning algorithm always has three components. That is representation, evaluation, and optimization. Representation. There are different ways to represent a concept, like in separating hyperplanes or graphical models or neural networks. We'll cover those things later. Don't worry if you haven't heard of those terms. And at the end of the day, you need to know how accurate is your machine learning algorithm, or how successful how do you want to evaluate your machine learning algorithm. Then we'll talk about accuracy or precision and recall, and other stuff, more complicated terms. And most machine learning algorithms use optimization, and there are combinatorial optimization like dynamic programming, and convex optimization like gradient descent, coordinate descent, and there's there's constraint optimization such as linear programming and quadratic programming. And the most commonly used algorithm is gradient descent. Gradient descent basically kind of goes towards the reverse direction of the gradient, so that it kind of is the steepest descent direction. And if the learning rate is small, it will converge eventually, but it will converge probably very slowly, like making small steps. But if the learning rate is too big, it's possible to diverge if it's bigger than 2 times the optimal learning rate, right? But if the learning rate is reasonable, it will eventually converge to the local minimum, not necessarily the global one. Okay, different types of learning scenarios. The basic type is supervised learning. For example, email filter classification. Then you need the training data to include the desired outputs. That is, the data has to be labeled, right? Each email should be labeled with its, outcome, like spam or not spam, right? Those data are kind of hard to get because you have to hire human beings to label them. Unsupervised learning kind of is better because it does not rely on those data that is labeled. They rely on unlabeled data sets. That is just emails, no label, right? So then you have tons of them very freely. Now, the typical example or more realistic scenario is something in between, right? You have a supervised set, which is small, like you have, say, 1,000 labeled emails, and then you have a vast amount of unlabeled data, right? So you want to seed your learning algorithm with the small set of labeled data, and then utilize the vast ocean of unlabeled data to improve its accuracy. Finally, there's a scenario called reinforcement learning, which is super hot these days due to like AlphaGo and DeepMind. In that case, there's no supervision for each step, but at the end of the day, there's a reward that you can observe. For example, if you play Go or chess, at the end of the day, you either win or lose. Or maybe in chess, you can also draw, right? You don't have the supervision of each step where should you go. But if you play a long enough sequence, you'll eventually observe a reward. So this is more like kids learning because they learn from rewards, either positive reward or negative reward. So supervised learning, that's the simplest case. We basically want to approximate an unknown function f based on a set of training data that is examples x, which is the data is example itself, and fx, which is the labeled example, right? So in the discrete case, it's called classification. For example, binary classification. On each email, you label f of x being positive or negative, being 0 or 1, like male or non-male. And multi-class, you classify it in image into one of the 10 digits. So the output is a number between 0 and 9. And sometimes you have structured output. For example, machine translation, your output is a string. It's a sequence, not a single number. So that's the most exciting area in machine learning, which we will talk about after midterm. The other case is when f of x returns a real number that is continuous. So that is called regression. For example, if you want to fit a curve. Now, when would supervised learning be the most useful? Well, there are several cases. The first case is when there's no human expert. So from some very difficult task, there's some data, but there's no human being that can, be very good at this problem. For example, if the x input is a bond graph for a new molecule and the output fx is the predicted binding strength to AIDS protease. I don't even know what that is, but probably nobody is good at that. But given enough data, machine learning can learn it. But a more common scenario is when human beings are good at it, but cannot explain it. For example, recognize face. Human beings are really, really good at it. But if you ask somebody, how did you do it? They cannot tell you. They're unable to kind of describe it in a very formal way, right? A lot of tasks in computer vision are like that. And the third case where the desired function changes frequently. So you have to adapt every single time you have new trends, right? So stock price prediction or spam filtering, right? Because right now you probably have a new type of frequent spams, which you did not observe 5 years ago. 5 years ago, there was another very frequent type of spams, which does not occur very often now, right? Or when each user needs a customized function, for example, spam filtering. Your filtering program must be different from mine because we feed it with different training data, right? Because as you label an email spam or not spam, you're actually giving the spam filter one more example to train on. So it keeps improving, keeps adapting to your personal need, right? And speech recognition, more typical, right? Because you have to adapt to your voice, to your accent, to your whatever, right? Now let's look at classification. Classification is the most common use case of machine learning. Most of the time, if you hear people talk about machine learning, chances are that they actually meant classification. Okay, so in classification, you classify an input X into a discrete output variable, right? Either spam or not spam, for example. And here, this example is that your image is your input, and your output is either sea bass or salmon. Okay. Now, it's actually important to notice that before we do any machine learning, we need to pre-process the data and then to extract features from the data. The features are basically observations of the data. And for example, in this case, we can use the length of the fish as a feature. And it turns out to be not a good feature because they overlap pretty much a lot. Lightness is probably a better feature because they overlap less. And sea bass is kind of known to be lighter than salmon. Another feature might be width. That sea bass are kind of on average wider than salmon, for example. So let's say you just use these two features, and salmons are here and sea bass are there, and you can draw the line, a linear separator, to kind of classify the two cases. Or instead of linear classification, you can also draw a non-linear curve as the decision boundary, like this curve, which is probably more accurate than this linear classifier, or kind of extreme that is a very zigzagged kind of a separator that is highly nonlinear. Okay, which one is the best? Which one is the worst? Well, I'll leave it as a question for you to figure out, and we'll kind of answer that question in the next part. Now, besides classification, you can also do regression. You can do linear regression, nonlinear regression, and this example is polynomial curve fitting with a certain polynomial degree, like say 0, degree 1, degree 3, degree 9. And we know that probably degree 3 is best for this data set. And degree 0 using a single flat line and degree 1 using a single line are probably not good. But degree 9 is not good either, right? So even though it kind of matches every single data point, but really it's very far off from the pattern in the data. So we'll also talk about which one is the best model in the next part. So here's what we'll cover. So this week we'll cover the simplest machine learning algorithm, that is nearest neighbors, or k-nearest neighbors. And next week and the week after, that is week 2 and 3, will be devoted to linear classification, perceptron and extensions. And then we'll talk about support vector machines, which is kind of the most powerful machine learning algorithm before deep learning. And then kernel methods to do nonlinear classification, and then structured classification. And then after midterm, we'll talk about unsupervised learning, clustering, k-means, and expectation maximization, dimensionality reduction, like PCA. And finally, the last week, we'll come back to supervised training and talk about neural networks and deep learning. Well, even though deep learning can be used for unsupervised learning as well, but we'll just do a little bit of intro of deep learning to just give you the flavor of how deep learning works.